Hi, welcome to Video and Control System. So, in this video, we look into solutions of few questions which have been asked in a particular test. So, these are the things you should know. So, you should know stability, root array, root locus, frequency response of system, which is Bode plot as well as the polar plots. Okay, with these, okay, let us go into the exact question what we are looking at. Okay, this is the question what we have. So in the first question A part, so there is a characteristic equation given. Del of s is given by s power 4 plus 4s cube plus 4s square plus 3s plus k equal to 0. We are asked to determine the value of k such that you'll get a sustained oscillation. So that is a marginally stable value. And for that value of k, what is the frequency of oscillation, and what is the range of k for a stable system. So what is the range of k for a stable system beyond 0? What is this x value? Okay, let us first we need to use the Rhodes array to solve this problem. So this is a characteristic equation. Let me write the Rhodes array for this. S power 4 s cube s square s power 1 and s power 0. The elements are, this is 1 4. Of course we need to write the alternate elements 1 4 a. Next it is these two, that is 3 and sorry 4 and 3. So this element is nothing but 16 minus 3 by 4 and 4 into k. This is 0 minus 0 by 4. This will become k now. So what is this? It is 16 minus 3 divided by 4 is 3.25. Okay, now 3.25 into 3 minus 9.75. 9.75 minus 4k by 3.25 then 0. Then you have k 0 0. So this is now coming out to be 9.75 minus 4k by 3.25 is equal to 0. So naturally 9.75 minus 4k is equal to 0. Then k is equal to 9.75 by 4. This, okay, 9.75 divided by 4 is 2.4375 is the value of k. So that this all elements of this row become 0, which means that system is ending with an auxiliary equation. So k margin is equal to 2.4375. So AFS is now equal to 3.25 square plus k margin equal to 0 is your if you find the roots of it, of course k margin is comes out to be is 3.25 square is equal to minus of k margin is 2.4375, then a square is equal to minus 2.4375 by 3.25, which is now divided by 3.25, which is minus 0.75 is the value of a square. So then the roots of s is under root of minus plus or minus 0.75. So what is square root of oh, sorry, this is square root of 0.75. So the roots are plus or minus 0.866. So this is frequency at which the system is oscillate. So that's what you had two parts. The two parts were determine the value of k such that it will end up with a sustained oscillation. That value of k is equal to 2.4375 for the first question. The corresponding frequency at which it will oscillate is 0.866 radian per second. For the second part of the question, so this is the first part. So for the first part, I have this as a k margin is stable is 2.4375. The frequency of oscillation is 0.866 radian per second, and for system to be stable, the value should be greater than 0, but should be less than 2.437. That's what is the solution for 1A. Right? Next, what is 1B? 1B is this. So the open loop transfer function GFS into HFS is given by 10 by S into S plus 3 S plus 7, and you are asked to find whether all the closed loop poles are more negative than minus 1. More negative than minus 1. So this is what we are asked to find. So in this open loop transfer function, if you make a unity feedback for this, you will end up with, so this is what you have. This is what you have. Is 10 by S into S plus 3 S plus 7. If you close the loop, this is your open loop position. Open loop positions are at 0, minus 3 and minus 7. Once you close the loop, they all will change. So this will go to X, this will go to Y, this will go to Z. What we're asking is, once you make the closed loop, does this XYZ pole positions of the closed loop poles, are they all more negative than minus 1 or not? For which I should find what is CFS by RFS, which is, for this, it is nothing but divided by S into S plus 3 S plus 7 plus 10. So this is what is. So if I do this, I'll get exactly where the roots are. So since the question given is, are they all more negative than minus 1 or not? So this is usually how the poles are. So this is pole here, this is minus 3 and minus 7. If I just draw a line which is corresponding to minus 1 point, then this becomes at plus 1, this becomes at minus 2, this becomes at minus 6. The pole positions will change when I shift this origin from this to this. So why I'm shifting this origin? I'm shifting this origin to verify whether the poles are more negative than this minus 1 or not. So once I change this transfer function will become GFS into HFS will become now divided by S minus 1, S plus 2, S plus 6. Now what is the, of course this is for the green y-axis, this is for, so this is, let me write as CFS dash by RFS dash. This is for a shifted origin, shifted y-axis, y-axis by 1 towards the left hand side. So to ensure that whether the poles are there at more negative than minus 1 or not. So then this becomes n divided by S minus 1, S plus 2, S plus 6 plus. So now this is your denominator. So let me find out. Let me write the Rhodes survey for this del of s. So what is del of s for this? So del of s is nothing but you equate this denominator to 0. Let me write as del of s dash. So why this is s dash? Because I have shifted my origin. So will it not become s minus 1, s plus 2, s plus 6 plus 10 equal to 0. If I just do this, it is s minus 1. So this will become s square plus 8s plus 12 plus. So this is now s. Okay, let me add this. this, let me not add this plus 10 here, let me write it as plus 10 later, because let me multiply this and then find later add x minus 1 into a square plus 8s plus 12 plus 10. So what is this? It is s cube plus of 8 square plus 12s, and it is minus a square minus 8s minus 12, then it is plus 10. So what is addition? It is s cube plus 7 square plus 4s minus 2 equal to 0. So now this is a new characteristic equation with your y-axis shifted by 1 towards left side. So let me write the root array for this. When I wrote the root array for this, this is s cube, s square, s power 1, s power 0. So it is 1, 4, 7 minus 2. So this is 16, sorry, uh, 7, 4 are 28 minus of minus 2 by 7, and it is 0, and it is minus 2, 0. Can you see this is now coming out to be, I think this is a positive number. How much is this? This is 30 by 7. 30 by 7 is 4.8. If you just have a look at this first column, so there is only one sign change. So one sign change in the first column of the roots array with this with this origin shifted, with this axis shifted. What does this mean here? So out of these three poles x, y, z, one is there lying somewhere here. One is there lying, of course, one is there towards the left hand, sorry, to the right hand side of this. So it has to be, because you cannot have it on complex here. So it has to be on the real axis. So it is somewhere here. So what is the answer for this? You have, the question was how many poles, let me see the question. What is the question? The question is whether all closed loop poles are more negative than minus 1. No, it is one closed, let me write it over there. One closed loop pole lies between 0 and 0 and minus 1, and other two are more negative than minus. So other two are lying here, one is lying between 0 and minus 1. So the answer is, so one pole is not more negative than minus 1, whether other closed loop poles are more negative than minus 1. So what is the next question? The next question is, what is the effect of addition of the open loop pole in the left hand side of its plane on root locus and stability? Okay, this is a bit of open loop, it's an open question. What is given is, assume that, so for this let us assume that you have a GFS into HFS, something like this. It is assume that it is K by some S into S plus 6 is there, plus 6 is there. So what do you have? You actually have a, this is how the poles will look like. So this is 0 at minus 6, and this will certainly break at minus 3, and it will go like this. The system is absolutely stable. Suppose if I add a pole here, the moment I add a pole here, this entire system will change. The system, what will happen to this? Number of asymptotes will become 3, and then we're going to have a different breakup point. When the number of asymptotes are 3, then it will go to right hand side. Here the system is absolutely stable. Absolutely stable. The moment you add this, so what will happen here? You have this, you have this, you have this. Okay, assume that you are adding it at minus 8. This is minus 6. What happens? It goes like this. This is certainly going like this. It breaks here, and then you can see the system will become conditionally stable. So the moment you add uh, a pole here, the system changes from, and for this particular example, this is not common for all. This is stable to conditionally stable system. The root locus will change like this. Fine. Let us consider to the same if I add a 0. If I add a 0 at s plus maybe wherever s plus 5. If I add a 0 at s plus 5, what happens? This was minus 6, and if I add a 0 here, add a 0 here, what happens? This certainly goes here and this goes here. The system was absolutely stable. The system remains in absolutely stable. So no change in the stability of the system, but the root locus totally changes. No change in stability of the system if you add add a 0 in this particular example. So if you take a different example, then it is totally different. And how does the root locus changes? Root locus changes from this to this. As I said, this is a purely open question. If you take a different transfer function, assume that if you take this transfer function, if I add a 0, the system which was conditionally stable may become absolutely stable. So that totally varies from transfer function to transfer function. Right? Okay. Next, let us see what the question is. Okay. This is 1C. In question 2A, what we have? In question 2A, we have a okay. So there is GFS into HFS given. So that's why mistake given as characteristic equation. So GFS into HFS is K by S into A square plus 6S plus 10 is given. Here asked to plot the root locus. Okay, let us try to plot the root locus for this. If you actually find the roots of it, so it will actually become K by S into S plus R minus 3, sorry, plus of 3 plus or minus J1, plus 3 plus or minus J1. So meaning, so I have the poles at origin. This is minus 3 and it's somewhere here. So it is J1 minus J1. These are the pole positions. Suppose now we need to find the asymptotes. Asymptotes are P minus Z, which is 3 minus 0, which is 3. Centroid will be minus 3 minus 0 minus of 0 by 3. So this is minus 6 by 3, which is minus 2. So have a centroid at minus 2. So the angles of the centroid are 60 degree, 180 degree and 300 degree, which is always fixed. This is 60, 180, 300. Let us find what is are there any because this is very close to real axis. So let us find what is angle of departure. Theta d is nothing but 180 degree plus phi, where phi is equal to summation of theta z minus summation of theta p. Of course, summation of theta z is equal to 0, whereas summation of theta p is equal to theta p1 plus theta p2. Of course, if you want to find it for this, so this is theta p1, this is theta p2. So theta p1 anyhow it is 90 degree, theta p2 is 180 degree minus of tan inverse of it is 1 by 3. So this is what is summation of theta p is 90 plus of 180 minus tan inverse of 1 by 3 close. It is now, you can see it is 251.5 degrees. That's what is theta p. Then phi becomes 0 minus 251.5 degree, which is minus 251.5 degree. So theta d is, sorry for that, it is 180 degree plus of excuse me, minus 251.5 degrees. So then theta d comes out to be, it is 180 minus 251.5. Sorry, it is minus, it is minus 71.5 degrees. This is the angle of departure. Let us also find at what point it just intersects the axis. For that we need to write the root survey. A root survey for this I can write it as, okay, del of s is given by, from this, so del of s is s into a square plus 6s plus 10 plus a equal to 0. This will become s cube plus 6s square plus 10s plus k equal to 0. Let me write the root survey for this, so which is s cube s square, which is 1 10 86 k. For 1 is 60 minus k by 6, this is 0. Then finally this becomes k 0. So there is a possibility that this can become 0. So 60 minus k is equal to 0 is a possibility. Then k margin is 60. That is a possibility of auxiliary equation. So auxiliary equation is 6s square plus k margin equals 0. Then what are the roots of the auxiliary equation? It is 6s square is equal to minus k margin, which is nothing but minus of 60, 6 square. This will go with this. So s square is equal to minus 10. Then x is equal to plus or minus of a root 10, which is nothing but plus or minus of a 3.16. So this will cross at plus or minus j 3.16. It is interesting to see, since the angle of departure is minus 71 degree, which is very, this is coming down like this is going up like this. So this is what is minus 71 degree from here, almost minus 72 degree. Since it is very close to the real axis, there is a possibility that this may break here. This may just meet somewhere here. So for that, let us find the breakup point. How do I find the breakup point? So to find the breakup point, let us find dt by ds. I should equal to 0. So I have the value of del of s as s cube plus 6s square plus ns plus k equal to 0. I can write k is equal to minus of s cube plus 6s square plus ns. So then differentiating this with respect to this will give you 3a square plus 12s plus 10. The roots of this happens to be, if I find the root of it, okay, so 3 and 12 and 10. Roots are minus 1.183 and minus 2.816. Okay, both these values are valid here. Can you see this is because the root locus exist here. The root locus will exist here. It actually exists in this region. So both are valid points. So it will actually come here and meet at meet at minus 2.816. It is that breakup point, and one will come here, the other will try to go this side. By that time this is also coming, they'll again break at minus 1.183. Once they break, so they will again become, they'll become complex and go like this. They'll become complex and go like this. So at what point they'll cross? They cross at plus j 3.16 minus j 3.16. This is what is the root locus. Actually, the root locus, it departs from this minus 3 plus of j1 and minus 3 minus of j1. It departs with angle of minus 72 degree here. This departs with angle of plus 72 degree, and then they actually break here. They're going to meet here at minus 2.816, which is one of the breaker point which we found here. And once they break, one will go to the left side, other will go towards the right side. When it is going towards the right side, this will again come and break at minus 1.183. Once they break, so it will become complex, and the roots will be guided by these two asymptotes which are there at 60 degree and 300 degree. This is taken care by the asymptote which is at minus, sorry, 180 degree. So we have, this is the entire problem. Fine. Okay, we're done with this. So what is next question? Next question is, you're asked to plot a polar plot for a unity feedback system having a transfer function, having an open loop transfer function GFS into HFS is given by 10 by s plus 1, s plus 2, s plus 3. So we are asked to plot the polar plot of this. Okay, let me just go here. For polar plot, we know that we need to replace x by j omega. This will end up with a magnitude of GFS into HFS, which is given by 10 divided by under root of omega square plus 1 square under root of omega square plus 2 square under root of omega square plus 3 square. This is the magnitude. The phase is given by minus of tan inverse of omega minus of tan inverse of omega by 2 minus of tan inverse of omega by 3. So how I am writing this is replacing all s by j omega. This is j omega plus 2 and j omega plus 3. Because all these are complex quantities, you are writing 1 over a plus bb can be written as under root of a square plus b square as the magnitude. The angle is minus of tan inverse of b by a. So where b is the quotient of imaginary, a is the quotient of real. That's what is this. Now let us give the value of different values of omega starting from 0 to infinity. Let us try to find out what is magnitude and phase. So it is 0, infinity. When it is 0, you see this becomes 0, this is 0, this is 0. So then this becomes, so it's actually omega is 0. So it will become 10 by 6. 10 by 6 is 1.66. And phase angle, if you substitute all these omegas as 0, it will be 0 degree. The extreme is when this is infinity, infinity, infinity. So anything by infinity is 0. That's the magnitude is 0. And tan inverse of infinity, we know that it is 90 degree. So it is minus 90, minus 90, minus 90. It is minus 240. These are the two extremes. Meaning, so this is, if you take it as 1 point, how much is 10 by 6? 10 by 6. Sorry. 10 by 6. 1.66. If it is 1.66, the angle is 0 degree. So you can see ultimately, since all these are negative, the phase, the plot moves in fourth quadrant, third quadrant, and it ends in second quadrant. This actually goes like this. So it goes like this, goes like this, and then goes with a magnitude of 0. This is what is the plot is. If you are very keenly interested what is the magnitude here, what is the magnitude here, you just find at minus 90 degree, minus 90 degree, what's the value of omega. Substitute that value of omega here and then find what it is. And make this equal to minus 180 degree, find omega 1 omega t, substitute the magnitude. Okay, that I can find here. What I'll do, I'll equate this minus tan inverse of alpha a minus tan inverse of 0.5 alpha a minus tan inverse of alpha a divided by 3, alpha equals minus 90 shift cal. So I'll get this omega 1. So it is coming out to be 1 only. So at omega is equal to 1, I'll get it as minus 90 degree. Did I equate? Okay. If I equate to minus 180 shift cal, so this is coming at omega is equal to, okay, let us find out it is 3.31. So if you substitute omega is equal to 1 here, so what is this? It is 10 divided by, open the parenthesis, okay, under root of, this is just for clarity, alpha a square plus 1, close the parenthesis into, open the parenthesis, square root, open the parenthesis, alpha a square plus 2 square, close into, open the parenthesis, square root of, open the parenthesis, alpha a square plus 3 square, close, calculate for 3.31. So the magnitude here is 0.166. Calculate for 1, it is 1. Calculate for a value of 1, it is, see, here the magnitude is 1, here the magnitude is 0.166. See now, this is how, but these are the extra 2 points. The polar plot is simply like this. This is a polar plot. At omega is equal to 1 radian per second, the phase angle is minus 90 degree. At omega is equal to 3.31, the phase is minus 180. This is at minus 180 degree. And the magnitude is 0.166. And here the magnitude is, so it's like, okay, 1 at an angle minus 90 degree. Omega is 1 here, omega is 3.3. So this is what is the polar plot. So just extra point, even if you write this much, so this is what is the polar plot. So this is the polar plot. This is at 1.66. This is minus 270 degree, this is minus 90 degree, this is minus 180 degree. This is the rotation. Fine. Okay, let us move to next. What is the next one? The next one says sketch the Bode plot for a closed loop system whose open loop transfer function is given by k by so and so. You are asked to find the value of k for a gain margin of 10 degree. Fine. So what is the open loop transfer function you have? This is 3a. Open loop transfer function you have is GFS into HFS is k by s into 1 plus s 1 plus 0.1 s. This is what we have. We are asked to find the value of k for a gain margin of 10 dB. Okay, let us find this. How do we? Okay, this is, sorry. Okay, let me find. Let us take k is equal to 1 and proceed with our plotting of the graph. So if k is equal to 1, then GFS into HFS will become 1 by s into 1 plus s and 1 plus 0.1 s. So magnitude at origin of omega zero point 0.1 radian per second will be the terms that are contributing a 20 log 1 minus a 20 log 0.1 is supposed to be 20 dB. And if you write the slope table of this, of all the terms, so this is what is you have from here, their cutoff frequency, their individual slope, resultant slope. So terms are 1 by s, 1 over 1 plus s, 1 over 1 plus 0.1 s. There is no cutoff frequency for this. This is minus 20 dB per decade. This is minus, this is dB per decade. This is radian per second. And this is having 1 radian per second as cutoff frequency. It is minus 20 and it is minus 40. Its cutoff frequency is 10. This is minus 20, again minus 60. So what will happen? You start with a magnitude of 0.1. This is 1, then 10, 100. Assume that this is your 0 dB line. This is plus 20. So how do you start? You start with this plus 20 with a slope of minus 20 dB per decade. So it just goes like this. And then at 1 you have a slope. So this again changes to minus. Here this is minus 20. This becomes minus 40. Afterwards it will again become minus 60 dB per decade. So this is how the plot is. I'll show you how the plot looks like on the Similog sheet. Let us also write the phase equation and find omega PC. Phase equation as per this open trans function is, as per this open trans function it is, this is contributing minus 90 degree. This is contributing tan inverse of omega minus of tan inverse of 0.1 omega. So now let us find out for different values of omega what is the phase. It is omega in phase 0 infinity. It is minus 90 degree and omega is 0. When omega is infinity, minus 90, minus 90, minus 90, this will become minus 270 degree. So it is certainly possible to get that minus 180 degree because the angles are minus, minus, minus. So it is found that it will happen at 3.16 radian per second. So what we'll do, I will show you the graph which has been already drawn. So this is what the plot is. See here, the plot goes like this. So this is 20 dB. So 20 dB down 1 decade, 20 per decade, and then 40 dB down per decade is 40 dB per decade. Slope curve, here it is minus 20 dB per decade. Here it is minus 40 dB per decade. Here it is minus 60 dB per decade. And then you are trying to identify that is what omega PC, that is omega PC, you can see it is 3.16 radian per second. I'm getting a magnitude of almost minus 20 dB. Minus 20 dB. So that's what it is. So gain margin with equal to 1 is minus of minus 20 dB, which is 20 dB. So now we found out what is gain margin with equal to 1, which is equal to now 20 dB. We are asked to find the value of K such that gain margin is 10 dB. So with K is equal to 1, you have 20 dB as a gain margin. So gain margin required is actually 10. So what I should do here, so I can see this is my gain margin. So this gain margin has to reduce to 10. So meaning that I have to have my new 0 dB line here. So this is my new 0 dB line. This is 0 dB line for a gain margin of 10 dB. You see now this is 10 dB. This is 10 dB. So for this to be 10 dB, so this new 0 dB line has moved from here to here by 10 dBs. So then by how much this has moved here? So this has moved by 10 dBs. So what will happen to this magnitude? This magnitude will become 30 dB. So now can I write what is the magnitude origin? It is 30 dB is equal to 20 log A minus of 20 log 20 log 0.1 20 log 0.1, that is yes. So if you find for the value of k here, what is k value? So now it is 30 alpha equals 20 log, sorry, 20 log of alpha a minus 20 log of 0.1. Shift and shift here. You get the value of k as 3.16. 3.16 is the value of k, so that you get a gain margin of 10 dB. Of course, there is another equation you have. So 20 log a is equal to uh, you have an equation like, okay, what is this? So you have gain margin with k equal to 1 minus given gain margin. So what is gain margin with k equal to 1? So it comes out by 20 dB. What are the gain margin that I have asked? They have asked for a gain margin of 10. So this is 20 log of k. So this is another way of finding. So there is no need to shift your 0 dB, all those stuff. So this is more conceptual way of shifting the 0 dB so that the gain margin becomes 10 dB. So then by how much they are shifting this down or up, by that much amount this will increase or decrease. If you are going up by 10 dB, then this will become 10. Why you are actually coming down by 10 dB? So that your gain margin becomes 10 dB. So because of that you are coming down by 10 dB. So this becomes 30, and then you substituted this, found the value of k as 3.16. The other way is use this standard equation. 20 log k is equal to gain margin with k equal to 1 minus given gain margin. So what is the given gain margin? 10 dB. This is 20 dB. So what is 20 log k? So 20 log k is equal to 10 dB. Find the value of k. So k is nothing but 10 to the power of 10 by 20. So what is 10 to the power of 10 to the power of 10 by 20? It's exactly 3.16. Get same value. You get the same value. This is how you can find the value of uh, a for a given gain margin. Okay, what is the next question? Sorry, the next question is here. Okay, the next question is you are asked to find the transfer function of this plot which is given there. The plot given is, okay, let me just take a sheet of paper. Okay, let me first write the plot and then show you what's happening then. So this is going up like this. So this is omega 1, this is 0.1, this is 20 dB, and this is 10, this is 30, this is omega, this is 0 dB per decade, here it is plus 20 dB per decade, here it is minus 20 dB per decade, here it is minus 40 dB per decade. Okay, let me show you this. This is the problem we have. So we are asked to find the transfer function. So we are asked to know what is GFS into HFS. If you can carefully see, the initial slope is plus 20 per decade, and there is no, of course, this is just keep going like this. So there is no frequency for this. So then this naturally happens to be 0 at origin. So it is K plus. You see now the slope is initially positive, it will become 0. So 0 dB per decade at omega 1. If we can see here, you can actually find what is omega 1 is. So this is zero point 0.1 and this is I think it is not given as 0 dB. It would have been given as 0 dB, so that's an issue there. So this would have been given as 0 dB, so this has to be 0 dB, otherwise we can't take it. So let us write this as 0 dB also, since it is going up by 20 dB and the slope is 20 dB per decade. So actually this omega 1 has to be 10 times of this, a decade of 0.1, so which is nothing but 1 radian per second. So at 1 radian per second I have a pole, so that's why it is 1 plus yes. And then there is a slope reduction again at 10 radian per second, so it is 1 plus s by 10. There is one more pole at 30 because the slope reduces from minus 20 to minus 40. This is just a first order pole. It is 1 plus s by 30, because here from plus 20 it will become 0 dB per decade, from 0 dB it will become minus 20, from minus 20 it will become minus 40 dB. So you have 3 poles and a 0th origin. So next we need to find the value of k. So how do we find the value of k? Since it is given as 0 dB, so at the 0 dB, uh, what is the value you have? It is 20 log of k plus of, why it is plus, it is a 0th origin. It is 20 log of omega, which is 0.1. Solve for k value. If you solve for k value now, it is 0 alpha equals 20 log alpha a plus 20 log 0.1 shift cal. So let us find the value of k. K value comes out to be 10. So there is another way of finding the value of k here. So at omega is equal to omega 1, the magnitude is 20 dB. So I can do this. This is 20 dB at 20 log. The terms that are contributing at omega 1 are again k and s. This contribution starts after omega 1 plus 20 log omega equal to 1 now. If you do this, now also you'll get the value of k as 10. Either you can use this equation or this equation to find the value of k. So what is the transfer function? Now this is now 10. It is 10s by 1 plus s into 1 plus s by 10 plus into 1 plus s by 30. This is the transfer function for the last question. That's how you can able to comfortably answer the questions corresponding to Rhodes array, root locus, and Bode plot and plot. Thank you.